Welcome to Math 154 videos. Today we're going to talk about Rolle's theorem, which is a special case of the mean value theorem, and how it's applied to showing an equation has a certain number of roots. So first I wanted to outline a couple of the types of problems we see in a section like this. So there's the first one showing an equation has at most a certain number of roots. There's showing an equation has exactly a certain number of roots, and showing that there exists a certain number of roots for an equation. So for our case where we have at most a certain number, we're going to use Rolle's theorem. So that means if an equation has at most a certain number of roots, it could have 0 or 1 or 2, but it can't have more than that number. So if we want to show an equation has at most one root, the strategy with Rolle's theorem is we show that it can't have 2 or more. So at most one root means it could have 0 or 1 roots, but could not have 2 or more. So if we use Rolle's theorem to show that it can't have 2, then it can't have more than 2, and then must have at most one root. If we want to show an equation has exactly a certain number of roots, first we need to find them. We can find a root by using the intermediate value theorem, which we learned back in chapter 2. And then once we've found those roots, we can show that there aren't more by using Rolle's theorem. Then the third type of problem is there exists a root. That's just the intermediate value theorem, which we have learned already. So if we want to show there exists a root, we just find it by using the intermediate value theorem. If we want to show there's exactly a certain number, we show there can't be more with the Rolle's theorem after first showing that they exist with the intermediate value theorem. And then to show there is at most a certain number of roots, we just use Rolle's theorem. So that's an outline of what we're going to be doing. So here's the example we're going to go over. Show x to the 5th plus 10x plus 3 equals 0 has exactly one real root. So this is the middle case in that chart I just showed you. We want to first show by the IVT, the intermediate value theorem, that we can find a root, and then we want to show by Rolle's theorem that 2 roots is impossible. Okay, so we want to show there's exactly 1, so we show that if there's 2 roots, that's impossible, so there can't be 2 or more. Alright, so we're going to start out with the intermediate value theorem. So the intermediate value theorem says if f is continuous, and we're going to check that first, it's polynomial, so f is continuous. And then we need to find 2 numbers, one such that f of some number is less than 0, and one such that f of some number is greater than 0. So let's go ahead and try f of 0. If we plug in 0 for x, we get 3. So we have a number that's greater than 0. So a good strategy for this is always to plug in 0, because 0 is the easiest number we can evaluate, and so it makes it a good candidate to plug in. Well, now we have something that's greater than 0, so we need to think about something that could give us something less than 0. Now, since we have 2 plus signs in our equation for up here at the top, then we're probably going to want to plug in a negative number for x. So why don't we try negative 1? So if we plug in negative 1 up here on the left side of our equation, which is going to be our f, then we're going to get negative 1 to the 5th minus 10 plus 3. And so that's going to be negative 8. That's less than 0. So since we have something greater than 0 and something less than 0, and f is continuous, then by the intermediate value theorem, we have some number c in the interval from negative 1 to 0. We don't want to include 1 and 0 because it's not 1 or 0, it's some number in between them. So we have some number c in this interval, 1, negative 1 to 0, such that f of c is equal to 0. And that's just because if we have some continuous function and f of negative 1 is down here, it's negative, and f of 0 is positive, then obviously we have to cross over the x-axis. So c is our root, and we found that one exists by the intermediate value theorem. So that's half of the problem. Now we have to show there can't be more than one. Now we're going to do that by using Rolle's theorem, and for Rolle's theorem we need to check that f is both continuous and differentiable, which it is. So we can just state that. F is continuous, which I'll abbreviate, and differentiable on all real numbers. And this is how we denote that with this r with a double bar. So that's all the real numbers, and f is continuous and differentiable on all real numbers because it's a polynomial. So we have that. Well, now we're going to assume there are two roots. And we're going to label them A and B. Alright, so we want to show the equation has exactly one root, so we're going to assume there's more than one. If there's more than one, that means there's two or more. So we'll assume there's two roots, A and B. Then f of A is equal to f of B, which is equal to 0. Because if they're roots, f of A is 0 and f of B is 0. That's what it means to be a root. So then, by Rolle's theorem, we have some number, and I'm not going to call it C because we already used C, so let's call it R, and R is in AB, and f prime of R is 0. Okay, and that's because if the equation has two roots, and this is our x and y axis here, there's no way we can connect these two with a straight line without having a place where the derivative is 0, where there's a horizontal tangent line. So it could be up like that, or it could be down here, and then we'd have a 0 tangent line at this point. So all we're saying is this is R. If these are our roots A and B, and R is in between them, and there's going to be a point where the derivative is 0, and it's going to be at R because f is continuous. Well, we're going to show now that can't happen. So, f prime of R, or not f prime of R, f prime of x is equal to x to the fourth plus 10. Alright? 5x to the fourth plus 10. So, if f prime is 5x to the fourth plus 10, any x we plug in here, when we raise it to an even power, it's going to be positive. So this is actually always positive. So, f prime of R being equal to 0 cannot happen. So we can't get f prime of R equal to 0. This is a contradiction. When we get a contradiction, it means that what we assumed, which was there are two roots A and B, is not true. So since we have a contradiction, there aren't two roots, which means there's less than two roots. So we found there are less than two roots, so that means 1 or 0, but in the previous part we proved that there actually was one by using the intermediate value theorem. Therefore, f, or this equation up here, has exactly one root. And we'll just write that down. And that proves our statement.